Hello calculus students, today we're going to look at a new series test. So far let's just run over our options. We can do telescoping series in order to find the limit of partial sums, sometimes involving partial fractions. That's all really just one technique though. Or maybe two if you don't do partial fractions and you just do telescoping straight off. Anyway, we've got that. We've got geometric series, which we always look for. We've got P series, which we always look for. Now we can compare one series to another if it seems like it's close to another known series. So it's close to geometric or P series, we can do comparison or limit comparison test. Today we're going to learn how to handle another kind of series that's, pretty common and really doesn't fit into any of those other categories, even the integral test. We're going to look at the alternating series test today. So the alternating series test works for series that are alternating between positive and negative. So for instance, a really simple alternating series would be this one right here. So you can see it's clearly going positive and negative, so some terms are contributing more, some terms are taking away from that cumulative contribution so far. So I just wanted to write this one out, so I think you could probably write this out different ways, but see if you can figure it out yourself. Those are obviously powers of 2 on the bottom, right? So we could say powers of 2, maybe to the nth power, powers of 1/2 then, yes. If we start at 0, then we'll of course get 1, except it's alternating. So I think there's a few different ways to write this. You could say negative 1/2 there, or you could put an alternator term like negative 1 to the n power times 1/2 to the n, right? So this is a clear alternator term. Sometimes you'll have it built into the power and have to pull it out separately, especially when you're working with the alternating series test. So let's get that out of the way. So if it's like this, you're going to want to pull out the negative like I just did there. So you can clearly see the alternating portion. Because the alternating series test says in order to use the test, you've got to form the series into either one of these two things. It could be with the alternator to the n power and then the rest of the series expression, or the alternator to the n+1 power and the rest of the series expression. You want to get it into that form because the way the test works is it says, well, an alternating series is going to converge if you meet two conditions. You got to meet both conditions. First, the limit as you approach infinity of the sequence has to go to 0. That shouldn't surprise you. That's kind of like the same condition that you need for like the divergence test that shows that if it's not equal to 0, then the series definitely diverges. So that once again says that the contributing terms as you go out get small fast. So that's one idea that should be pretty familiar. And this other idea should also be pretty familiar. What's this say? I mean, there's heavy symbolism here, but it's something that we've used for other tests as well, like the integral test. It says that the next term has to be smaller than or equal to the previous term for all n belonging to the natural numbers, for all n bigger than some specific n bigger than the natural numbers. You could all pretty much just put for all n belonging to the natural numbers, but as long as it's true that you are, in other words, decreasing, of course, that's what this condition says, for some spot in the series. If you're decreasing after that point for all n, then you're good to go. So you got to be decreasing after some specific finite point in the sequence, and you've got to have your sequence limit to 0. If that's true, then the alternating series will converge. So let's write this as the decreasing condition that we're so familiar with for other things. If you want to use a derivative instead of a sequence argument there, you can. If you want to show the derivative's decreasing for all values after a certain spot. And then let's call this the sequence contributor gets small. Okay, same conditions we've seen before, so it shouldn't be too surprising. Let's look at 3 examples. So this first example, luckily, is already written in that form right there, so we don't have to do any alteration to the form. In other words, this is really just the alternating harmonic series. This is a harmonic series that alternates. So the harmonic series, of course, is famously divergent. So does this one converge or diverge? Well, remember, we kind of ignore the alternator part and we check the 2 conditions. So the limit as n approaches infinity of a sub n, which is 1 over n, does that go to 0? Well, yeah, clearly, I mean, yeah, that's like the simplest limit ever. Of course, 1 over something infinitely large is infinitely small, or 0. So, check. We got condition 1. Condition 2, if I go 1 over n plus 1, is that smaller than or equal to 1 over n? I don't even think I really need to do any more math on that one. That's also really true because the denominator over here is smaller. Excuse me, the denominator over here is larger, so the fraction is smaller. If you really want to see it, I guess you can cross multiply, and that's really obviously true. So pretty much that's a little demonstration that therefore this series converges by the alternating series test. Yes. All right. So let's look at another one. So this guy, the alternator is not clear right now. So I first need to rewrite it with the alternator clearly exposed so that I can look at the sequence without the alternator contribution. So the alternator is going to come from this negative power, right? So this is negative to the n minus 1, so let's just write that separately. So we've got 2 to the n minus 1, and then we've also got a negative 1 to the n minus 1 lurking down there, right? So what's that? That's going to be 1 to infinity n over 2 to the n minus 1. This is really just times negative 1. This is on the bottom, so I could go like this, right? Yeah. Okay, so let's see. So if I factor that out, yeah, it's going to be that. So this is an alternator term. I don't think you really need to clean it up. It doesn't match exactly like that does. Let's think about this. This is a 1, right? So 1 power. Does it really matter if I have this here or not? I don't think it does. I think this is the same thing if I erase that. Think about that for a second. I think you'll be good because of the specialness of 1. That really doesn't matter because 1 reciprocal is still 1. Yeah? Okay, so now we've got it in the form of one of those guys, and I think we should be good to go. So it's not exactly like that, but this is clearly an alternating term. So, all right, so we need to look at the pieces. Condition 1 says that the limit as you approach infinity of the sequence, this part, has to go to 0. Question is, does it? This is an exponential function. Yeah, it's got a little bit of a shift, but of course that goes to 0 by bottom order of magnitude is much greater. Exponentials grow much faster than lines. The bottom is growing much, much faster, so as we approach infinity, it's going to be bigger, so we're going to get 0. If you want to show that with L'Hopital, because it's infinity over infinity, go ahead and by all means do that. Okay, so check. Condition 1. Condition 2, is it decreasing after some spot? So let's see. If we go n plus 1 term, that's going to be that. And n minus 1 plus 1 is 2 to the n power. Is that smaller than that? I'm really not sure right now, so definitely going to put a question mark there. Let's, I don't know, should we do a little bit of cross multiplication? So I'm going to go n plus 1 times 2 to the n minus 1 is less than or equal to n times 2 to the n. Let's see here. So, yeah. Distribute. I could break this apart. These both have n minus 1 power. You know, before distributing, I'm really just going to break this power apart and see if that yields anything. So this is 2 to the n times 2 to the negative 1. Nice. Now I can cancel that out on both sides. So now I've got n plus 1 and 2 to the negative 1 power is 1/2. So that is less than this. That says n plus 1 is less than or equal to 2n. I think that's definitely true, right? Multiplying by 2 is definitely going to be more than just adding by 1. Let's see if it's true for all n or whatever. So if I put in a case of n equals 1, then we've got 2 is less than or equal to 2, check mark. If I put in a case of n equals 2, then I've got 3 is less than or equal to 4, check mark. That's definitely true. So I guess I should put my question mark. I wasn't sure here. I wasn't sure here. I wasn't sure here. I'm sure there. That shows that it's decreasing. So we've met the assumptions of the alternating series test. So let me just erase some of this stuff now. Got it down. Just to free up our notes. So I'm going to write this one out a little more formally. So this guy converges since the limit as n approaches infinity of a sub n is 0, and it is decreasing for all n belonging to the natural numbers. Remember, if it's decreasing after 2 or 3, you're still good to go. So thus satisfying the convergent conditions for the alternating series test. There's another way to write it out. Okay? Let's look at one last example before we look at the alternating series remainder theorem, which is really simple. So this last one is already good to go, right? We've got the alternating terms separated out. It's clearly an alternating series. We could take the limit of the sequence. Now the limit of the sequence here is 1. That's not equal to 0. So already I can see that this fails the alternating series test. I'm going to have to try to do another test on it, and I think it's beyond our ability to do right now. So yeah, I think really the limit as you approach infinity, if you include that alternating term, isn't it really, if you include the alternator, the limit as you approach infinity of this whole thing is going to go to 1, and this is going to alternate between +1 and -1. So since plus and -1 aren't 0, I think by the divergence test, this diverges by the divergence test. You could say it that way. Let's just show that it's also, let's see if it's decreasing, just for the heck of it, just to see. So a sub n plus 1 is that less than a sub n, I don't know. Doesn't even really matter now, but just for the heck of it, in case it asks you. So that'd be what, n plus 2 over n plus 1 is less than n plus 1 over n. I think, well, that's not sure yet. So cross multiplying, we're going to get n squared plus 2n if I go like that. And over here I'm going to have n squared plus 2n plus 1. Chop, chop. So I've got 2n is less than or equal to 2n plus 1. Here I wasn't sure. Here I wasn't sure. Here I'm sure that that is not true. So this is also not decreasing, so it radically fails both conditions of the alternating series test. So let's look at the alternating series remainder, because whether or not it converges is one thing. What it converges to is not something alternating series test can do, but you can really quickly and easily, using alternating series, come up with an estimate on what it converges to if it does. So let's look at that. Okay, so the last thing I thought we'd look at is the alternating series remainder theorem. It says for if you have a convergent alternating series, this is the same kind of argument we saw for the integral test, you put absolute values on here because you want to just think about the absolute value. Don't worry about that too much, but the remainder, which is the sum minus the sum of the first however many terms you stop at, the remainder in an alternating series, it turns out, is less than or equal to the very next term. And I think if you start thinking about some examples and write it down, this will really make a lot of intuitive sense. Because of the alternatingness, and you kind of have some terms absorbing some of the next terms, the remainder is always going to be less than or equal to that. So let's use that to approximate the sum using 6 terms or so, and see how close we are to that convergent value of this example. First, we better make sure that it's actually a convergent alternating series. Let's not write it down, let's just kind of do it in our head. This one's pretty easy. So we've got an alternator clearly already separate from the sequence expression that we're going to take the sum of. And there I wrote out the first however many terms. We've got a factorial on the bottom here. So the limit as n approaches infinity of this is clearly going to go to 0 really, really quickly, in fact. So check on condition 1. Condition 2 says, is the next term going to be less than the previous term every time? I guess we could write that out. So are we going to have a sub n plus 1 less than or equal to a sub n? So let's go 1 over n plus 1 factorial and compare that to 1 over n factorial. Remember, factorials you can write like this. So simplifying the factorial, like we learned in a previous lesson, is that. And I think we're dividing by a factorial on both sides, so we're going to cancel that out. Let's see what's left. So we've got 1 over n plus 1 on the left-hand side, and 1 over here. That says 1 is less than or equal to, multiplying up, n plus 1. That's, of course, true for all n belonging to the natural numbers, so we're good to go. This guy is a convergent alternating series. Let's try to be a little bit more specific about what it converges to using the remainder theorem for this one. So the remainder theorem says, if you look at s sub 6, let's see, I've written it out this many terms, let's do that. 1, 2, 3, 4, 5, 6. So first of all, it says the remainder for the 7th term, or excuse me, the remainder, if we look at only the first 6 terms, that's going to be less than or equal to term 7. So term 7 here is, put 7 in, you get 8. That's going to make that positive, and 1 over 7 factorial right here. So r sub 6 is less than or equal to 1 over 7 factorial. I don't know what these factorials are. 1 factorial is, of course, 1. It's 2 times 1, 3 times 2, 4 times 6, 5 times 24. I think the next one's 720. Let's make sure. 6 times 120. Yep, and then that times 7. So we're going to have 720 here. This guy's going to be 5,040. So what this shows, and let's write that as a decimal. Well, I don't even need to write it as a decimal. So what this shows is the remainder after taking the first 6 terms is going to be less than or equal to 1 over that. So a pretty really small remainder. So this says the actual convergent value of the sequence, excuse me, the series, is going to be between 2 things. You're going to be between s sub 6 plus that remainder, and s sub 6 minus that remainder. So s sub 6 we can figure out by just adding up those first few terms, so let's do that. So we're going to have 1 minus 1/2 plus 1/6 minus 1/24 plus 1/120th minus 1 divided by 720. There's s sub 6. So we're going to have 0.6319 minus the remainder that we came up with. Same number here. Same number here. And you can see we've already got, after only 6 terms, we've got a really good estimate on the value that this alternating series converges to. So let me go to my notes and pull out those numbers real quick. So I just got that this was like minus 0.0002. I guess we could just stick it in our calculator. So we're going to go that minus 1 divided by 540. There's the lower bound, and we're going to go that plus 1 divided by 540. There's the upper bound. So we've got a really good estimate after using only 6 terms and little computational power for the convergent value of this series. I'll see you next time. If you guys want to just work on your alternating series problem, go through your assignment and try to get those done. We'll look at the other thing. Unless you want to do it on your own, it's pretty simple. That's convergent, series that are either absolutely or conditionally convergent. It's pretty easy to get those out of the book yourself, so it's up to you. That assignment won't be due until Wednesday when we come back. So just make sure you do the alternating series part and you should be good. See you then.